Well, hello everyone. Please say hi if there's anybody there. Hopefully, you guys can hear me well and you can see me well. So let's give it a few seconds just in case anyone else is interested in getting in. Say hi if you're listening to me in the chat room. Like, for example, something like this. Hi. This is the first time that I do a live stream, so I expect a lot of technical issues. If you're getting in, you can start typing in your questions so we can have this Sunday discussion. Hopefully more people. It says here that at least there are 2 people viewing. Perhaps many other people forgot. ¿Qué pasó?
¿Estás en mudo?
Sí.
No, estás en mudo.
¿Qué pasó?
¿Quieres que lo atraviese?
No.
Quiero checar algo de la privacidad de mi video.
Este.
Vuelve a bienvenida. Transición.
Hello, everyone. Well, we're gonna start. I don't see any questions yet, but even if there's no many people in the live stream, I'm gonna start explaining what the video today is gonna be about. Uh, the motivation for this video is that I noticed a lot of misinformation in Twitter primarily, but as well I noticed that many YouTubers were confused about what the technology of binary genomics does in comparison to other technologies, for example, the PacBio or Illumina sequencers. Let me introduce first myself. My name is Fabian Flores-Jasso, Flores-Jasso, if you want to call me like that. I got a PhD in biomedical sciences many years ago, maybe like about 15 years ago, and I studied biomedical sciences. So and I work at the National Institute of Genomic Medicine. And everything you are going to hear here today is my opinions only, and I don't represent the institution that I work for. But I know about genomics, more about what most layman people know. So I feel entitled to help to disambiguate a lot of things that I've noticed in the people interested in the sapphire, especially people interested in the sapphire because they're interested in the stock price. Okay, so what I'm gonna try to help you guys to understand today is why is it that we need mapping in genomics. Uh, and as I've said several times in Twitter, the software mapper is, as its name says, is a mapper. That means that it's not a sequencer, just like the PacBio, for example. Their technology, the PacBio technology, is mainly used for sequencing, and the Illumina technology is used for sequencing as well, and as well as QIAGEN and Thermo and other companies. Uh, and around the genomics industry, there's a lot of different tools that you can employ to understand or to identify things buried in the genome. And the things can be something interesting from basic science. It could be something related to disease, for example. And we are living very exciting times because the term genomics is already being very popular. The Nobel laureates last year were Jennifer Doudna and Emmanuel Charpentier, which invented, so to speak, a tool for editing the genomes much more easy than what we scientists were used to do before that discovery. And you all know this, like the tool for editing the genome is called CRISPR. But the system CRISPR already existed in the nature for millions of years. But the scientists managed to figure out a way to employ it to edit genomes. So since then, the term genomics and gene editing become very popular in the mainstream media, and you hear this everywhere in the news, and there are people that have nothing to do with genomics at all became related to the term because many financial institutions started talking about it. For example, ARG, and this is why many people who probably never thought they would be interested in genomics now suddenly they're interested in genomics, right? So, and because of this reason, I see that there's a lot of misunderstanding of what the technology of the Sapphire does in comparison with other systems, for example, the PacBio or the Illumina. And Illumina and PacBio are more related to each other than what the Sapphire is related to PacBio or Illumina. And I think all this started when some of the first publications using the PacBio machine uh, were used instead of PacBio and gave better results. So when that happened, many people took it the wrong way and started thinking that the Sapphire mapper is much better than the PacBio, which in certain ways it is, but it depends on what you use it for. So what I'm going to tell you about is why is it that we need to map the genome, any genome, not only the human genome, any genome, in order to understand its sequence. All right. So let me start by using an analogy for all of you. So most of you most likely have at least once in your life have tried to assemble a puzzle. So let me put this image here. All right. I'm gonna try to use this analogy. Imagine the genome is a puzzle. Okay? And if you have a puzzle, the only way, or the easiest way to assemble the puzzle correctly is first, you need to know how many pieces are in the puzzle. And second, you need to know the image that you are going to assemble. If you don't know the image and you don't know the number of pieces that you're going to assemble, I'm not saying that it's going to be impossible, but it's going to take a lot of time to figure out the image that you're supposed to make. So let me take this as an example. In my house, my wife likes, and my daughter, they like a lot puzzles. So we have this puzzle here, and imagine the genome is a puzzle. So this puzzle has 1,000 pieces. Okay, so we already have information about this puzzle. It has 1,000 pieces. Imagine if you have to assemble a puzzle, but you don't know how many pieces does it have. And imagine that you have a puzzle that you don't know the image that you're going to make. It could be nearly impossible. But one thing that all puzzles that we know have is two pieces of information. First is the number of pieces that it has, and second, the image that you're supposed to make. All right? And there are puzzles that are very simple to make, like this one that I have in the image, in which the pieces in the puzzle are large and there are not too many. Okay, and the image is not very complex. All right. Say for example that you have this other puzzle with more pieces, but still the image is not very complex. In the background, you will have the picture that you're supposed to make, and a lot of those pieces are actually what assemble the puzzle. In that puzzle, you will see that there are many pieces that look alike, all right? That are yellow, like for example these two, or there are more orange, like these other two, or there are more greenish, like these other two. And there will be other ones that will look very similar to each other, like for example this one here, this yellow one, and this other yellow one. All right? If you don't have any context at all of these two pieces, it will be very, very difficult to find the spot in the image in which they go, unless there is only two possible spots, yellow, in the entire puzzle. But if you have more than one spot that is yellow, it's going to be difficult to know which corresponds to which. All right? When you start to assemble the puzzle, the easiest way to start is by framing the edges. All right? Because by framing the edges, you already know what is already contained in it. And you already know that it's not larger than that. And everything that is left belongs to the inside, to the puzzle. Okay? So when you start by looking at the edges. And finding these edges, you will see that some pieces will have a blunt end and another one that corresponds to another piece. And this is pretty much what we do in sequencing. If you want to know the sequence of something, it's better, the larger it is better to know the edges first. or to have a map representation. In this case, the map is the image that you're going to make. All right? So the image is a figure, and it has two characters, and it has a tree, and it has the grass and the sky, and it has something that it looks like a house behind it. So that is the image that we're going to try to make. And imagine, like, for example, the PacBio machine or the Illumina machine or any other technology for sequencing, like each individual piece in the puzzle. And not only that, each individual detail painted in each piece of the puzzle. That is sequencing. The sequencing in this case relates to the fine detail of every piece in the puzzle. However, if we want to look at the whole image, it's very difficult to know how you have to assemble these small puzzles, these small pieces, into the puzzle to make a coherent image of it all. All right? So let's make a pause here and see if there's anyone trying to get in the stream that can't. All right. Seems that some people are there, but I don't see many people in the stream yet. So there is 4 current viewers. Okay, well, anytime. Hey, hello, vibes. If you want, you can start typing in. I'm just trying to finish this analogy of why we need maps when we do genomics. So in this image, what we have is, as I said, the puzzle, right? And we started to assemble the puzzle. But what if, for example, we have something more complex? Say, for example, this image, this puzzle. You might say, well, this image is not complicated. Well, it is if you break it in pieces. Because when you break it in pieces, and you find pieces that are this small, and you have 2 pieces that look very alike and are almost identical, the same color, it's very difficult to know where it goes. Do they go, for example, when you try to assemble the puzzle, do they go in here? Or do they go in here? Or do they go in here? For example. Or do they go over here? Well, it could be easier, for example, if you pull another piece, like this color, and say, well, most likely this color corresponds to the little angel, right? Inside, somewhere. So I know that it doesn't belong to the sky. However, does it belong to the belly? Does it belong to the leg? Or which angel does it belong to? That is the problem. See? And the sequencing technologies that we have so far, they'll look at the fine detail of each piece. So, for example, the genome is super huge. And if you have 2 pieces that look alike, if you look super close to each other, you will see that one has a blunt end. So one corresponds to an edge, and the other one doesn't. So I know that one corresponds to an end, but there are a myriad of those. Which one corresponds to what end? To what age? See? To what side of the frame? And the other one, which side of the sky does it belong to? Where does it belong to? It's very difficult. If you look close to it, you might say, well, it might be that this piece might correspond to this side of the puzzle. But for that, we need the whole image, right? For that, we need the whole image. If you don't have the whole image, it's very difficult. Now imagine, well, don't imagine, this is a fact. The image that we try to assemble has 4 different elements: A, D, G, and C. Those are the only 2 elements. So imagine a puzzle with 4 colors. Or imagine a puzzle with millions of pieces, all of them having only 4 kinds of shapes. If we look at these two pieces of blue, what you will see is that their shapes are not identical. One has an edge, this one has an edge, and the other one doesn't have an edge, a blunt edge. Okay, so these two pieces are different. But in the puzzle, there will be some that will be identical, and there will be some that are not identical, depending on how they make the puzzle. In the genome, we have only two, so we have only four. So the chances that we find highly repetitive patterns in the genome are very high, super high. So if you start by sequencing only, you'll find a lot of trouble trying to assemble the whole picture. And this is, for example, one of the troubles that the consortium of the genome sequencing project had in the 90s, before they finished the first draft of the genome. The first draft of the genome, the human genome sequence, had as a first aim to map the genome, and that's why it took 10 years to achieve. And there was another project related to the human genome sequencing that was made by Craig Venter and Cellular Genomics, and they believed differently. They believed that, in fact, you don't need mapping for the sequencing, and you can start sequencing massively, like something that they called shotgun sequencing, and then you figure out how to assemble the big pieces. But the problem was that at that time we didn't know how highly repetitive some parts of the genome were going to be. So for those highly repetitive sequences, we might never know where they belong to. And what I mean 1,000 times or 1,000,000 times in a row, T, or A, 1,000,000 times in a row. And that will be equivalent to this region to this region. It will be very difficult to know which region belongs to where. Okay? So for that, scientists at that time thought that it would be better, much better, if we created a map first. And what I mean by a map is if we know how the whole picture looks like, and then once we know that, we can try to figure out the fine detail, which is the sequence. We can try to figure out which of these pieces belong, because they're not entirely exactly identical. All right? So for that, this is why mapping and sequencing are complementary to each other. Let me see if I can see a question. Can you expand on the 4 types of genomes? And there are millions of variations, but you said that there are only 4 types. Okay, no, my mistake. I didn't refer to 4 types of genomes. I referred to four letters in the genome. So if you have an alphabet, in the Western alphabet, we have A, B, C, D, E, F, G, letters up to Z. Okay, so I guess that is 27 or 28, depending on the alphabet, on the country that you're looking at, on the language that you're looking at. So those are the letters that we use to communicate to each other in written and spoken language. But the genome doesn't have that many letters. The genome has only 4 letters, and that is A, T, G, and C. And in the genome, which is composed by the desoxyribonucleic acid, DNA, usually 1A pairs with a T, and a G pairs with a C in a complementary manner. So every time you see an A, you have a T, and every time you see a G, you have a C. And for example, you have ATGC, and on the other side, you will have TACG, which are complementary to each other. All right? So that's what I mean by 4-letter alphabet. And imagine that repeated billions of times, which is actually what composes the genome. I don't know if that ended up being explanatory or not. Well, that is what we. Let's continue with the explanation of why we need mapping. So what the Illumina sequences, what the Illumina machines and technology does is they look at the fine detail in small pieces, like this, which is very good if you study the precise sequence of small pieces of nucleic acids. For example, small pieces of DNA, or small pieces of the other kind of nucleic acid, which is RNA, which is what I study in my laboratory. If you want to look at those, Illumina is perfect. But the Illumina technology has figured out a way to make these pieces slightly larger. So imagine these four pieces bound together, these two pieces bound together with another 8 pieces. So you have a bundle of 10 pieces. So in that case, you will look at the picture of each piece, but each piece will be larger. So if you're looking at one part of the genome, for example, let's say this part over here, only where my finger is, you will see that there is blue, dark blue, light blue, and skin color. All right? If you look at that intersection, it will be very easy to assemble. Well, relatively easy to assemble. But if you use those pieces to look, for example, at this other part of the genome, which is sort of dark blue, it will be difficult to assemble. If you look at this other region where my finger is, it's only skin color. So that'll be difficult. For that, we will need probably a tool that can look at it with a bigger piece, with a much bigger piece. Instead of 10 small pieces like this, we will probably need something that can assemble 100 of these pieces. 100 of those pieces will give you, for example, the skin color of an entire foot. And we will say, oh, look, this piece of this color belongs to an entire foot, because I can see the fingers, and I can see that the fingers are above a cloud. So that will help us to understand quickly that that is a foot. But what if, for example, that piece of the genome, even as large as a foot, actually falls on this side? If it falls on this side, it would be difficult to know if it is where my finger is, or here, or there, or actually on the other side. PacBio, what it can look at is at the size of a foot, for example, at the size of a wing of that engine. But it's not going to look at bigger pieces. So for that, you need different technology. And this is where the Sapphire comes in. If you have a tool that doesn't necessarily look at the fine detail, we need to find the tool that is going to tell you how the whole picture looks like. Because that whole picture is going to tell us what we have to assemble. And what we have to assemble is a painting of two angels kissing each other over clouds. That is the ambiguity that we have if we don't have mapping. If we have mapping, what we have is we have big chunks of the genome assembled, and those big chunks of the genome, what tells us is there are two heads, so there are two individuals. There is two wings only on this side, and there are two wings on the other side, and there's one wing on the other side. And this big piece of cloud that we have here is underneath, it's not on top. That is what it's going to tell us. So this is why you need mapping. Now, does the Sapphire sequence? No, so far it doesn't sequence. And why is it that people started using PacBio to map then? If it's not good for mapping? Well, because it was the only tool available for knowing the sequence and the mapping at the same time. But it's not because it is suitable for mapping. Imagine that you're off-road, and the only vehicle you have is a Lamborghini. Would you use a Lamborghini or would you walk? Well, depends. If walking takes much longer time, then I would use my Lambo to go off-road. But are you gonna wreck the Lambo? Most likely. Are you gonna go probably with a lot of hurdles? Yes, most likely. So what the Sapphire does is an off-road vehicle, especially designed for being off-road. Uh, all right. Let me see. I see another question. It's a dumb question. For commercial applications, why do I hear that OGM will be the future for clinical tool of choice as replacement for initial diagnosis rather than acting complementary with sequence? That's a great question, and that is exactly the purpose of why we're here today. So when you try to do diagnostic test, genetic diagnostic test, the best tool will be, of course, that uh, we sequence your entire genome and tell you exactly what mutations you have that might cause you, for example, disease. Unfortunately, that is not possible yet because we don't understand a lot yet of what is um, for sure going to give you a disease. We might have a certain percentage of certain mutation causing diseases, but everyone is different to each other. And the only thing that belongs to you, the only thing that belongs to you is your genome, the sequence of your genome. Even if you have an identical twin, your genome sequence is going to be only unique to you. And it's going to be very alike to the one of your twin brother, but it's not going to be completely identical. So the only thing that it belongs to you and is unique to you is your genome, not even your ideas. It's your genome. So ideally, in an ideal world, the best will be to sequence every single genome of every single, but that in reality is not possible. I'm not saying that it's not going to be possible ever. I'm just saying that it might not be possible in our lifetimes. But we have other tools. So, for example, you go to the hospital because you suspect that your newborn or that your soon-to-be child might have a genetic disease or might have a disease. You look for information that can tell you what might be wrong with your child or with you. For example, if you suspect that you're developing some disease, and a lot of diseases have roots in the genetic sequence. So when you go to the clinic at the hospital, the type of analysis they do is not sequencing. First of all, because it takes time and it takes a lot of money for that. And not all the hospitals have this technology. For example, when my daughter was born at the hospital, they didn't offer this service to us, at least because the insurance that we have didn't cover the sequencing, and it was way too expensive for that. Even though we had technology, and my wife and I are both scientists and knew about this technology, and actually we are users of the sequencing technology of Illumina, the hospital didn't offer that as a service. What they did offer, though, was karyotypes, regular chromosome microarray, and another widely employed use is fluorescent in situ hybridization, which is FISH. So you will hear most of the time you will hear two different kinds: it's karyotype and FISH. And for those, you will need a microscope, and you need certain techniques to perform this genetic test. The drawback of those is that you pretty much know nothing about the genes that are affected unless you try specific probes that you imagine your genes might be compromised to. So you need to know something about your genetic disease. If you are blindfolded and you don't know anything but you suspect, it's very difficult that you're going to have results that tell you something about the genetic disease. For that, you need to employ several different tools, all of the ones I mentioned earlier, in combination. So what, in my opinion, what the Sapphire is going to replace is not sequencing. What the Sapphire is going to replace is these tools that are used already in the clinic, because the Sapphire is way faster than that and much cheaper than that. So, for example, a FISH test or a karyotype test take about from 2 weeks to 4 weeks. And you will only look at certain traits of the chromosome rearrangement. For example, the karyotype is the least specific. The most specific is a microarray, or the fish, for example. But the fish is highly specific, so it's not high throughput. So that means that we need to do several tests of fish in order to figure out what is wrong with your genes. And maybe, most likely, if we already know a lot of those conditions, you will find them. If we don't know about those conditions, you're not going to find them. And that's the big advantage with the Sapphire system, that you can detect chromosomal rearrangements that cannot be detected with the other tools. All right. So, in my opinion, it's going to be a big hit in the clinic because it will replace. If I had a clinic and I do karyotypes as a service, in no way I will keep the karyotype. I will trash them all, and I will buy only sapphires. But that is what I think, for several reasons. First, you will cover the entire genome, and it takes 400x coverage of the genome, which is huge, and you can do that in less than $1,000. In a karyotype, if you go to the service, it will be somewhere depending on the country you are. It could be from $1,200 to $2,000. What they claim is that they can do it for less than $1,000. So it's much faster, much more precise, and cheaper. What else you need? It's a no-brainer. Let me see. Hope that answered your question. Let me see. Thank you for doing this. You're welcome. Take the Jeep. Yeah, exactly. You take the Jeep. You don't take the Lambo. Mr. Invest a lot. Yeah. Kudos to you, my friend. Makes sense now. Clean that with the Sapphire 2. Thank you for doing that. Great. Let me see. Shoot me with your questions. This is replace the initial. Exactly. So imagine this is not going to replace PacBio. To be honest, if someone has a PacBio in a clinic and wants to replace the PacBio with the Sapphire system, doesn't know what it's doing. The truth is that you will have them both. You will have an army of sapphires and you will have an army of PacBios, or you will have an army of Illumina systems. That's what you would do. Actually, my graduate student, which already is finishing his graduate degree, and he started a business on his own. He's very into the Sapphire because what they do is genetic testing, and what they do is genetic testing with Illumina sequencing and another technique that is called QRT-PCR, which is highly quantitative. It's a highly quantitative tool to measure specific genes. But with a QRT-PCR, you don't look at the whole genome. With the Sapphire system, you look at the whole genome. They stretch each individual chromosome and tag them with a fluorescent probe and say, this is how the picture has to look like. Now, once you have that and once you assemble that, now you look at the fine pieces and see if what is wrong exactly, nucleotide by nucleotide, with your sequence. But for a quick diagnostic test, I think the Sapphire is unbeatable. Let me see. Let's try another questions. Why don't we give it another 10 minutes and then we're done for the session? Try to shoot me as many questions as you can. How do you think Sapphire has utility for CRISPR technology? That is something different. The CRISPR technology is the tool that you use to edit the genome, to edit the sequence that is wrong with you. That is the main difference. The Sapphire and the sequencing technologies that we have is to figure out what is wrong. The gene editing is the tool that we need to fix it once we know what is wrong. Okay, but The Sapphire system is going to look at the whole picture, and it's going to look at the whole picture from this distance. The sequencing technology is going to look at the tiny pieces at this distance. So you need both. And depending on the type of rearrangement or mutation or error or mistake that you have in your genome, it will imply that the mutation of this can be fixed with CRISPR or not in the future. Not yet, but in the future, I think it's going to be a very standard technique at any hospital. Not necessarily to fix what is wrong with you at the genomic level, because we haven't figured out quite yet how to do that safely. But perhaps if you look at the picture at the movie Gattaca, we're pretty close to get to that. How close? I was less than 10 years. We're getting there. And actually, there's people who have done this already in China. There's newborns already that have been edited using the CRISPR technology. So we're very close to it. So most likely our grandchildren, some of them are going to be edited before they are born. CRISPR edited for gene editing, not for initial diagnostics. That I answered that already. What type of sequencer do you need? Do you think BNGO is working on with a pattern, short read, long read, full genome? I think it will make sense. It will make sense to have it attached to a long read. I don't know exactly, because technology companies are very secretive, and of course, we don't know exactly what Illumina is working on right now. And I have friends who have worked at Illumina, and they can't even talk to their colleagues, and their computers have these specific screens in which, in order to see what you're looking at, I don't know the name of those, but in order to see what you're looking at, you need to be straight up in front of the monitor. If you are at an angle, like a colleague coming to say, "Hey, do you want to have lunch or something?" they cannot see your screen. So it's completely secretive. So I don't know exactly what they're what they're working on, but to me it will make sense that is long read sequencing. That's what my bet is. But I wouldn't be surprised that it can figure if the most reliable one so far, and the one that has the biggest market share, at least for users. So, for example, in our institutions, we have a lot of Illumina sequencers. We tried to one PacBio a few years ago, but it was huge. And not only was huge, it was super expensive. So it was huge, and we couldn't fit it into any room in the building, and actually was very heavy if we didn't have a freight elevator to put it on the 5th floor in our building, which is where the sequencing technology is in our building. So we had to use the budget for other stuff, and you know how things work in academia and in the government, and my institution is something in between academia and government. So we had to employ the budget. We had a deadline to use the budget, so we said, okay, so let's go for another Illumina then. If we can't even install it, then we use it. Now the PacBio machines are smaller, the size of, for example, like a fridge or something. But the other one was like 3 or 4 fridges in a row, and it was more than a ton. So we couldn't even fit it in the room. Let me see. What other question? Do you think? Do you think? How do you think that it competes with CRISPR technology? The Sapphire doesn't compete with CRISPR technology. It's actually the first step to figure out what is wrong with your genome. The CRISPR technology is what you use in the end to fix what is wrong. But the mapper and the sequencing technology, Illumina and PacBio, are the tools that you need to figure out what is wrong. Then after you do that with whatever tool you like, then you use the CRISPR. Let me see. what are some pros and cons between Sapphire and 10x Genomics? Okay, tool for single cell sequencing, but it's not a sequencer. That is something that is actually that was something that when we called them for the first time to show us their technology, we thought that they will do single cell sequencing. It's not a single cell sequencer. What it does is a machine that isolates single cells, and then you do the sequencing. With what? With Illumina or PacBio or whatever other tool you want, but it doesn't do the sequencing itself. It does isolate single cells that then you use to build the library that we call them libraries, that you isolate the cell, extract the DNA or the RNA, and then you do the library to be read by your sequencer machine, Illumina or PacBio. So it doesn't compare to either sequencing or mapping. So it's a tool that is an intermediate step. So it can be employed. Yes, it can be employed. You isolate single cells, and then those single cells, I think, in theory, it could be possible using the Sapphire system. Because in the Sapphire system, you use single molecules of DNA arranged with a nanopore, with a nanonosole. And then you stretch them, and then you tag them. So if you can do that with individual sequences, I bet there will be a way to do it using single cells, okay? Because every single cell has one genome, and it has 23 pieces of the genome from your father and 23 pieces of the genome of your mother merged together. And this is why it makes you. Let me see another question. I hope that wasn't more confused than it was. I remember you talking about your thoughts that Sapphire will be huge for plants and crops. Can you elaborate? Yes. So we tend to think that the genome is only human. Well, no. Every single species in the planet, and even things that are on the border of being alive, for example, viruses, have a genome. Bacteria have a genome. So the type of regulations that you need to use this in the clinic to diagnose diseases are different than the type of regulations that you need to, for example, say if certain type of cattle are of a certain species, of a certain lineage, or of a certain race. Or, for example, say that you have transgenic crops. But there are, for example, I'm going to make up things. Let's say that you have 20 different types of transgenic corn. And all of these have a different genetic landscape that are easily describable by using the Sapphire system. So if you want to sell or buy certain type of genetic modified crop, how do you know quickly if what you're getting or what you're buying is actually what you're saying you're getting or buying, right? So you will need a quick test to say that. Some people use PCR or microarray, for example. And for example, I remember several years ago, I was talking to a colleague who actually he does genomics for a living. He's the head of the genomics department and the Biotech Institute here in my country. And he told me that when he tried to open a sequencing facility, a private sequencing facility, one of the first clients that he had was someone who had a lot of livestock, and he was talking about how he can tag each of the race. I don't know anything about that, but how to tag differently different groups of cattle that he had in cows, because he had several races. And for example, for meat, you will eat several kinds of different animals that we don't necessarily see them when you go to the supermarket. You don't know that. But for example, you will see probably that it says certified livestock, US certified. That certification is that uh, type of cow belongs to a certain type only and not another. All right. So that type of certification, I think, is huge. I think the market is huge, and if you translate that into veggies and agriculture, I think the market, at least because of the type of regulation that it needs, that is less cumbersome, in my opinion, is less cumbersome than treating human disease. I think the market is much more big. There's one we start to get out and start cash flowing. What should buy and focus on next order to expand and grow? I don't know. That I don't know. But what I can tell you is what I saw in Illumina, for example, which is pretty much the business model that Tom Nash and others have discussed in YouTube. Illumina first started. When I talk about Illumina, is because Illumina is the biggest genomic technology provider in the world, and they have a very good company, but it wasn't easy in the beginning. So the first company that started doing sequencing at a massive scale was Roche, actually, and they had a machine that was called the 454. And that machine used a technique that was called pyrosequencing. And that pyrosequencing was great when they first did it, but the Illumina system was better and cheaper. So what they did in the beginning, these two companies, what they did in the beginning is that they will go to institutions and try to sell their machines. But the business was, like some other YouTubers have said, is that you look at the printer industry, is not in selling printers, it's in selling ink. So Illumina understood that very quickly and changed their business model to selling the ink. So, for example, if you want to start sequencing using Illumina machines, what you do is you rent or you ask for the machine, and then what you buy is the consumables, and then you provide the service. So I think that is what BNGO is doing, and if they want to grow, I think that something very obvious is FDA approval, because if they get FDA approval, many other regulation institutions, different countries, see that and take it as a good sign, and then approval in all other countries follows FDA approval. So if you have a machine that does mapping, say for example as well sequencing, and is FDA approved, you will have much better likelihood of being one of the huge competitors in the market. Because if I want to open a genetic testing facility or clinic, I don't need to certify myself and the technology that I'm using, because the technology that I'm using is already certified. And that is what Illumina did with one of their sequences. Say, like for example, I think it was about 2012, 13, they had one of their sequencers FDA approved, so people can use them in clinics. So if you want to open a clinic, you don't need to certify the machine because it's already certified. You only need to certify your clinic and your protocols and your standards. So that is what I think they have to focus on next, on FDA approval. I mean, so far what we have seen is very clear. More news like this, like the one we had last week about a science paper detecting many more chromosomal rearrangements compared to PacBio. Yeah, we're gonna see that in the next year, because that was what we saw with PacBio, and that was what we saw with Illumina when they first came into the market. And actually, we saw that in academia in the first 5 to 6 years. So almost every week for the next 5 to 6 years, you're gonna see one after the other, one of these types of news. Let me see. What are some? I answered that already. What are your thoughts on Simon thinking that devices such as BackBio is the future and Sapphire is just a niche and it won't have the widespread adoption? Do you think? Yeah, as I said, what is going to disrupt what the Sapphire is going to disrupt is the use of karyotypes and microarray and fish technologies for genetic testing. Those three are pretty much being replaced by Sapphire machine. Sapphire machine does not sequence, so it's not going to disrupt sequencing technologies unless the technology is adopted so that it can map and it can sequence at the same time. If it can do that, with high sensitivity and precision enough to match or better PacBio or Illumina, yeah, we can see adoption. But as I said, I don't know what BioNano is working on. As all technology companies is very secretive, and I have no ties at all with any of these companies. So I don't have any insider information, and I don't represent any of those as well. What I would probably think is that they will try, at least they will try, or if they're not trying already, to couple and integrate the Sapphire system to a sequencing in parallel. See, so that you don't need to have two different machines to do the job. Why is that important? Because if you need two different machines, one for the mapping and another for the sequencing, you need twice at least the sample that you need to get the results that you want. You need one volume of the sample for the sequencing and one volume of the sample for mapping. Why is that important? Because imagine if you have a tumor and they take a piece of you in your tumor, you take a piece of you for the sequencing, and that's it. But if they need twice the amount, that means that they need to take twice the piece of you that they need for the mapping, right? So I think it makes things more complicated, at least from the standpoint of the patient. And from the standpoint of the technical analysis, it would require two different sets of knowledge and skills. And for example, if you do the sequencing, the type of analysis that you have to do after your sample is prepared, put into machine, and then read, and then get the sequence done, what you get from the machine is a bunch of data. Is a bunch of data in gigabytes or terabytes. And so after that, you need to do an analysis, and for that you need someone who's specialized in genomic data. In my laboratory, part of my lab is used for genomic sequencing data, and we analyze databases and we analyze our own data. But those guys don't necessarily know how to operate the machine and how to extract the sample. They don't necessarily know how to do that. So the more machines you need to do the thing, to do the job, the more people you will require to do the whole thing. So the better is that these are integrated in a single line. And that's one of the other advantages of the Sapphire, that you don't need special skills for bioinformatics, because the software is integrated in the machine, and when they install the machine, it comes with a computer, with a laptop or something like that, and it comes with the software. So you don't need to do Unix or any other language for bioinformatics. You don't need special skills for that. So that's another advantage. Let me see another question. What we concept from Sapphire and 10x genomics, that I answered that already. The nanonosal patent turns up into a sequencer. It's both long and short read. I haven't read the patent, that patent specifically, but what I read pieces of it. So my suspicion is that everything is set up so that it can be turned into a sequencer, but it hasn't been finished yet. If they had it already, we will know already. So the one thing is when I'm telling you this because I'm familiar with patents. I've applied patents. So one thing is when you apply for the patent is that you probably did some test already, but you have the patent. So and and the, all the claims that you have in your patent, you have to make them work at a large scale. So I have no idea if they've made it work already, but I'm sure if they made it work, we will know by now. We will know by now. So that's what I can say about the patent. What are your thoughts on Simon? That I answered already. What are some pros and cons? You answered that already. Would you hire Simon as your assistant? No, I don't. I don't hire assistants. Although they're useful, I guess, because then you can say all the crap that I don't want to deal with, you deal with it, right? So if there's something that I don't want to do, all this paperwork that I don't want to read or sign, or I don't want to give these interviews, or I don't want to explain why I'm not invested in this or that, you deal with them. That is useful. Uh, but I think I don't know Simon personally, but I do like his responses in Twitter. Enthusiastic guy, and he looks like pretty like the type of guys that I like to have in my team, right? That are always trying to understand and to know, and they highly participative and all this. So I like that. I like that. And the people that I have in my lab pretty much are about his age, 20s, early 30s. So I like that because it's exciting to work with people like that who are passionate about what they do. Because sometimes it has happened to me that some people made it to my lab, and they're not passionate about discussing what I like to discuss. And those people, I don't like to have them in my lab. But Simon, he seems pretty passionate about the life sciences in general, not only genomics, but in general. Um, After the pandemic, do you think consumer curiosity and demand is building to look for genetic predispositions to disease, comorbidities? We will see every day people spend. Yeah, I see that, especially when 23andMe and other companies or other institutions start putting out the data that said, hey, you, because you are who you are in genomic terms, are more susceptible to get this type of disease. I'm sure people will look at it. And the truth is that the only thing, as I said before, the only thing that belongs to you is your genome. The only thing that and you will have it only until you're gone. But the only thing that is unique to you is your genome. And in your genome, there's an amount of information that we haven't been able to figure out entirely. But every month, every week, every year, we understand more, and the information that is buried there is very exciting. And I became that 5 years ago, 6 years ago. I became that, and I thought that a lot of things that I noticed in myself, in my personality, were learned because of my background. But I see my daughter, and I see a lot of things that I have never taught to her, never ever taught to her, and she does exactly the same, exactly the same. So the question is, was that learned, or was that in her genetic information? And this is why her personality or certain traits of her personality are like this. Um, Who knows? But we will know. That is the point. We will know. We are getting into there. We will know. Um, what could Sapphire tell a healthy person about their genome or possible future health issues? What it can tell is what we can tell already, that depending on the disease, you have a likelihood of developing that disease if you don't have it already. But is that 100% certain that you're going to have that disease or that trait? No. What it means is that you have a likelihood in a percentage of developing that disease. So some people will like to know, and some other people don't necessarily will like to know. I don't know, for example, if I want to do a 23andMe test because I might not like what I'm going to see. So, for example, if they say that there is a high probability that I develop lung cancer, I don't know if I want to be thinking, oh my God, is it today the day I develop it? Is it today? Is it today for the rest of my life? I don't want to know. But another part of me says, hey, what if I can take precautions for that? What if I get treated, if there is some sort of treatment, before that happens? What if I can change my destiny, so to speak? See, I don't know. I don't know yet. I haven't decided yet. But there are some people who do like to know, and there are some other people who have decided that they don't want to know. But what it can tell is what we can tell so far. So it's not only the Sapphire system. For example, 23andMe has the largest database of genetic data in humans. I believe it's about 10 million people already, of all races, of all ages, of all backgrounds, of all everything. So the information they have is huge, huge. So and actually academic papers that have been published using the genomic database of 23andMe, they reveal information that is wow. There is like, oh my God, why don't we know this? Why isn't this in the mainstream media, for example? Because that information is important. The one thing I do notice though is that I've been interested in genomics even before the term existed. So actually, one of the reasons why I studied biomedical sciences is because that convinced me to study biomedical sciences because I watched the movie Gattaca when it came out, and I went actually to the movie theater and watched it, and probably, and by that time, uh, that the plot in that movie was that we at some point we will know what's in our genes and how to prevent diseases, and even certain traits, phenotypic traits, like for example eye color or hair color or height, for example. So there will be a point in which we will have to decide if we want that or not in our society. We're very close to it. They already did it in China. They fixed two twin girls that were born. They fixed them. They removed certain type of mutation that came from the father. Okay, so they did it in China, but there will be every country in the world will have to make their own decision because the time will come to decide if we want that in our societies or not. So it is good, from my perspective, it is good that Jennifer Doudna and Emmanuel Charpentier won another prize because that will make the conversation to start in the common crowd because we need to decide what we want. To be honest, in my opinion, that will happen sooner or later. That will happen. But what I think is important is that when we decide collectively if we want that or not, we do it with information uh, in hand, so that when we decide what we decide, we at least are aware of the advantages and the possible consequences, not only blindly going for it or not because it's good or oh no my God, this is bad, you're playing God. No, I think we have to make an informative decision, right? And I think it's great that Emmanuel and Jennifer won the Nobel Prize last year, and I think it's great. RG is talking about genomics, and I think the BNGO is being taught as well, and I think that is great because that will make people aware of that, and I think it's great that 23andMe is going public, because you will see 23andMe. Yeah, I think is a very interesting company, and I think that um, 23andMe is going to put in the discussion something even more important than what Facebook and WhatsApp and Google has put into over the table, which is access to privacy. And make no mistake, 23andMe hot, so to speak, uh, very important for society. And the society that we know so far is going to change. It's going to change, and data and privacy are going to change. Life insurances are going to change. Health insurances are going to change because of the genomic information. Because of that, only because of that, and because of the access that we're going to have. And have you heard about Google Genomics? Well, they give you tools and storage to put your data in. So the more we sequence, which is an advantage, the more we have to store, which is a disadvantage, because you need a lot of storage for that. So if I understand the point that Simon and Ark are doing about sequencing, which is ideal, but the amount of storage that you're going to need for that to store each individual data is going to be huge, 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 huge. Actually, there is a movement that is thinking in the opposite direction. Is that, hey, we have a lot of information that we have collected in the world about everything, about sciences, about art, about every single possible piece of knowledge that humankind has ever made. But we don't necessarily have the amount of storage that we need to store that. In all the literature that Google is, for example, storing in bits, not in paper, right? Because it's getting faded if you keep them in pieces of literature of ancient books that are being digitalized. And they say, hey, isn't it true that the genome can store a lot of information? Why don't we try to store this information instead of bits? Why don't we try to store it in nucleotides? Because the genome sequence can be stored in hundreds of books this thick, and that is what is contained in a single cell. And a single cell is tiny. Why don't we use the human genome or a genetic code to store all that information that we have in letters, in common alphabets? That's an idea. In that case, we will need very small space, like a room or something, to store all the information in the world, because then we can deconvolute it and translate it back into an alphabet, into a regular alphabet, not a 4-letter alphabet. So that is one thing. Let me see another question, because we are taking long. What is your BNGO stock price projected in a year? I don't predict stock prices. I don't know that. I don't know anything about what the prices of BNGO or any other stock are going to be. What I can tell you about is the situations that I imagine based on the technology that is being developed. That is what we're here for. I'm sorry. I know that most of you want to hear my price prediction for BNGO or any other stock, but I don't know. That's the truth. I have no idea. In your opinion, will Sapphire ever get to a mass adoption worldwide and it be just research tool? No, I think it will be an adoption worldwide, but I think that will depend not on the Sapphire, but just as Illumina and PacBio are not worldwide adopted tools in the clinic, just like that. um, but not because it's not going to be adopted. First, we need to pass certain regulations for Sapphire or any other tool, right? So I think, in my opinion, I think it no longer depends to Sapphire. I think it depends on the people that plan and that foresee the use of Sapphire in the clinic, not of bio-nanogenomics. I think they're doing a great job. It's in a matter of time. But I think, as I said before, what I think they're going to disrupt is the use in the market of uh, microarrays, chromosomal microarrays, for sure, fish, and karyotypes. Karyotypes is an ancient tool that we've been using, and is labor intensive, and it doesn't give you much information. So the first tool that I will trash is karyotypes. I will leave, if I had a genetic testing facility, I will leave microarrays, and I will leave fish, because with that you can detect certain things that I'm sure not necessarily Sapphire can detect. I'm sure there will be a few, but karyotypes immediately I will get rid of them and substitute them with Sapphire. Would it be better for Sapphire to merge with bigger companies like 10x Genomics, since it has more diverse solutions? I don't think, if I had to if I was on the Sapphire team, I don't think merging with a 10x Genomics company like would be the best move. In my opinion, and this is only my opinion, I think it would be a much better move if they merge with a company that has the technology to sequence. What companies have this? Illumina, PacBio, Kaijin, Thermo, uh, Oxford Nanopore. Um, yeah, those are the ones that come to mind. That they made the technology, and they don't step on each other's feet, because they have their own technology to sequence, right? The next genomics, as I said before, they don't sequence. They isolate. At least the main product they have is they isolate individual cells, and they have a technique to isolate the nucleic acid contents of those individual cells. And then you use that to build a library that you're going to put into the sequencing instrument. And the sequencing instrument is Illumina, PacBio, Oxford Nanopore, is this other technology. So they are an intermediate step in the technical handling of the sample. So that is what they do. Pattern turn Sapphire into a sequencer. Mr. Invest a lot. No problem. I researched Illumina FDA approvals. I noticed not a single machine that has blank FDA approval. However, Illumina holds FDA clearances, authorizations for specific applications, LTDs. They have one. They have one machine. I don't remember the name, but they have one machine that it can be used in the clinic. That's what I know, because we have one of those. And actually, I read the news when the FBI called 23andMe and said that they cannot provide clinical uh, clinical advice. I'm not quite sure if this is the correct term, but they couldn't offer any health information about future um, diseases that people might develop. That was in the 2012 or 13. I was very mad because I knew that it was possible, uh, and I thought that the FDA was making a mistake. And a few weeks or months later, it came the FDA approval for one of the Illumina machines. I don't remember the name, but as I said, 10 years later, we have one at our institutions. And one of those you can use it in the clinic, and it's FDA approved for its use in the clinic to detect certain types of diseases. So that I'm completely sure. Yeah, this is extremely informative. You're welcome. Who is your number one? Who is your number one competitor? Of who? Of me? I don't have competitors, alas. Not that I know of. Maybe there are some competitors that want to compete with me, but I'm a scientist. I don't have competitors. I have colleagues who either discovered what I was looking for first, or I discovered what they were looking for first. But I don't call them competitors. Snapseed is going to take some of our share in digital cytogenomics. I don't know. I mean, it could be. It could be. That will depend. But as far as I see it, uh, the software system has its own niche, and it's not going to compete much with other technologies that I. So it could be, but I'm not I'm not entirely convinced that is going to happen. What actual clinics are PacBio used in? That is something I don't know. I don't know what clinics use PacBio, but they have a lot of customers. But to be honest, I tell you a little story. When when my wife was pregnant with my daughter, we did a test that is called the chorionic villi test, in which they take a little piece of chorionic villi, and they look at the cells that they could collect. They look at them using genetic tests. One of the genetic tests they used was fish, I guess. I'm not sure if they use fish or they use karyotypes. But what they look with these tools is large chromosomal rearrangements. So, for example, what they look is at trisomies. That is, that you have an extra chromosome. So, for example, trisomy 21 is a genetic condition in which you have an extra chromosome. Which chromosome? One chromosome, the chromosome 21. This is what trisomy 21. So they look at a large pieces of information, and is very. I think it's very simple to look at. If you look at the number of chromosomes that you have, instead of finding 46, you have one extra chromosome, or actually two extra chromosomes. Instead of 23 pairs, you have an extra chromosome. So that is very simple to do. And even though the technology for deep sequencing was already available, at least in academia, and I pretty much knew how to do the analysis at that time, the service at the hospital didn't include sequencing as a genetic test. But it didn't include at that time, not because the technology didn't exist. Because my daughter was born in Massachusetts when I worked at the UMass Medical School. And actually, we had at the UMass Medical at that time, we were one of the first universities in the world that had one PacBio, not PacBio, sorry, 454 from Roche, and we had Illumina sequencers. So we knew that the technology existed because we were users of that technology in my lab, in the lab that I worked when I was at the UMass Medical. But the same hospital at the UMass Medical didn't offer sequencing as a service. And I was, what is wrong here? What is going on here? Why is it? The truth is that our health insurance didn't cover the cost of sequencing. That was the truth. Because the technology existed, the point is that if your health insurance, because of what you pay for, is going to cover the cost of that service. So if your health insurance covers it, you can start sequencing everyone. So I am a strong advocate to start sequencing every single newborn in the planet right on. I'm an advocate of that because that is when we're going to start understanding what makes you get old, what makes you stay healthy, what makes you develop diseases. We're going to start to understand that. So far, we don't have that because we don't have a metric in real time of ourselves. The closest to that is something similar, for example, to this, in which you're trying to have a record of yourself, of your heartbeat, of your moves, of your movement during the day, how many calories you do. But imagine if you can do that and you can collect a piece of sample from you and make an analysis over time. So, and not only from genes, as well from hormones, as well from osmolytes that you ingest, for example, or that you accumulate in your blood. So once we start doing that, things will change drastically. Unfortunately, that will come first for people who will be able to pay, not for everyone. Just like in most countries in the world, we don't, not all people get access to the best health technology. Right? Let me see. Is there a point of ever making a mapping technology that can see an even higher range of base pair, or is that? I'm assuming that BP is base pair, or is that not necessary? So I'm assuming that BP is base pair. Is there a point where mapping technology that can be seen an even higher range? I hope it will. I think it will. But the truth is that, um, to be honest, I don't imagine how. I'm sure that it is, but my intelligence and my knowledge doesn't take me that far. Even though in my lab at the institution that I work at, we have projects that aim to develop Illumina system works for sequencing. And we develop projects that we aim to file for a patent for, and then we aim to license to Illumina so they can do better what they do in their sequences. I can't imagine how we can enlarge the length of the base pairs that we can have a sequence for. And the reason for this is that any technology that we use uses some sort of hack of nature. So the Oxford Nanopore, the PacBio, the Illumina, all that use some sort of hack that already exists in nature. For example, these nanopores are pores that are made of amino acids are passing the piece of DNA that is going through, right? Through nanotechnology, we can sense the little change in ion current that goes through every single reaction that of an addition of a nucleotide or not. And for the Illumina one, we use polymerases, the polymerase, and make the pieces of DNA that we're going to read using the fluorophores that we invent, right? And for the PacBio, we use a polymerase to read one piece and read back the complementary sequence. So we use some sort of hack of something that already exists in nature. And unfortunately, since we use that, and we haven't invented completely out of nothing the tool that is going to read an entire chromosome at once, base by base, because actually nature hasn't made it yet. In millions, billions of years of evolution, nature hasn't made it yet. I don't know if it's possible or not, but it doesn't exist in nature yet. So we need to be clever than nature. And alas, we as humans, we're not. We're not clever, more clever than nature. So I don't know. I hope it will, but I don't know. I lost every second you went to answer my Illumina question. I'm trying to catch up. Unfortunately, is that the question that I researched Illumina FDA? Is that the question? I know, well, the answer is I know for sure that Illumina has at least one sequencer machine that is FDA approved for its use in the clinic. With CCOs will make it possible for governments to cover reimbursed genetic testing with the Sapphire. I hope so. That's the key point, and I think that is the greatest news I've heard from Illumina, that is actually possible. I believe that this could be possible because the service that you can provide by using the Sapphire system is much cheaper than any of the other sequencing tools. And actually, I think it's going to be cheaper than doing a karyotype, to be honest. So if it's cheaper doing a BNGO analysis than a karyotype, and the karyotype is the most useful, one of the most useful tools that is already employed in the clinic, is better for a health insurance to pay for to cover the Sapphire system instead of the karyotype or the fish analysis. And not only that, it can cost you half of what it's going to cost you for the other two, and it's going to be way faster. So you can have the results in hours. The other ones, you're going to have the results in weeks, from 2 to 4 weeks. The karyotype takes probably like about 3 weeks, and the fish takes about 2 weeks, and it's more expensive, and it is precise, and it is less precise. So it is a no-brainer. That is what is going to disrupt, not the sequencing. It's going to disrupt that market. So I don't see anyone buying another karyotype machine or an instrument for doing karyotypes instead of a Sapphire. I honestly don't see it. And if they do, it's because they don't know what they're doing, to be honest. Base pair. Yeah, so BP is base pair. Yes. So I guess then I answered question. So let me see if there's another one on top that I didn't answer. Or if you guys felt that I didn't answer any of your questions because I might miss some of them, you can paste it here. Or if this is why we need mapping. So the point of the point of this talk is to tell you why is it that we need mapping. And mapping does not compete with sequencing unless you're using sequencing to do the mapping, which is what people have done in the past for PacBio. Since they didn't know the picture that they were looking at, they used sequencing of PacBio to do the mapping. Of course, if you do that, it's a very bad tool to use. It's very useless. But if you use something that is specific for mapping to map, it's going to map better than the PacBio machine. Now, you use a mapper to sequence, it's not going to sequence anything. So, for example, the molecules that I study in my lab are small RNAs, in particular, something that is called microRNAs. So for that, the Sapphire system is useless. So if I ever try to do some sort of microRNA analysis using the Sapphire, I'm going to be completely, that's completely useless. But if you use a Sapphire to map instead of PacBio to map, of course, the PacBio is going to miss some last 2 months that Sapphire is much better to map and catches more rearrangements that the PacBio couldn't catch, right? But if you use the PacBio to sequence, if you use the Sapphire to sequence, you're going to be in trouble because you're not going to see anything, right? So each of these tools is specific for what they do. It's just like if you ask me, what is better, a car, a boat, or a motorcycle? Well, it depends on what you use them for, right? You can't use a motorcycle or a car in the river, or you can use a boat in the river. So you use an appropriate tool for what you want. And this is exactly the case for the SAFI and PacBio. Another question, is it possible for a third-party company can create software that mapping and sequences companies can use and build integrated workflow instead of each company trying to reinvent the wheel? Yes, absolutely. And actually, I think I'm completely sure I'm completely sure that there are some companies that are working on that. And actually, I would probably bet that BioNano is working on that as well. How to integrate that more easily so that you don't have two separate things and you have to figure out how to um, assemble the data together coming from one or the other. So I'm completely sure. And if not, if there are no companies that are doing that, the community, the scientific community will do it. And much likely, those tools are going to be freely available in either GitHub or any other repository of or scripts. Yeah, that will happen all win-win. Yes, absolutely, that will be a win-win for everyone. So, in my opinion, before you guys have the last questions, in my opinion, uh, I think it would be a good idea for Illumina or PacBio to make an acquisition attempt of BioNano genomics because it's a no-brainer. It's a no-brainer, and it doesn't make sense uh, to not have a tool that maps. So imagine this: Illumina tried to acquire PacBio in a bold move. When that happened, I was like, these guys are going to have the monopoly in the industry. If they were already the biggest ones, this makes them unbeatable. For some reason, the deal didn't take place. You can read anywhere if you want more information. But none of them has a mapping technology. So PacBio wasn't acquired. A few months ago, Thermo tried to acquire Kaijin. And if they did, Kaijin has its own sequencing technology. And Thermo has its own sequencing technology because they acquired it from Lab Technologies, who acquired it from Invitrogen before that. So Thermo has a big piece of the life sciences market, life sciences in general. And genomics is one part of the life sciences market. But the key point here is that the genomics of the entire life sciences tree and branches, the genomics has the potential to come to the public sooner than any other branch of the life sciences in general. Has the potential to get sooner to the public and to have an impact in society very soon. But there is one thing that none of them have, which is a mapping technology. A mapping technology. Whoever has that first is going to win over the other ones. Whoever has that. So is it going to be Illumina? Well, maybe they are one of the strongest ones. The only one that matches Illumina in size of a company is Thermo. So imagine if Thermo can map as well, and they can couple that and integrate that with their sequencing technology, they win. If it's Illumina, they win. If it's PacBio, they win. So who's going to be? And maybe, I don't know, I have no idea, but maybe PacBio will make an attempt, and maybe BioNano Genomics will accept or will reject the offer, which is a likelihood event. They might reject the offer because they are working on something bigger than that, but who knows? So I have no idea. I think it's a very interesting times. What I can be pretty sure is that at least one of them is going to try to acquire Bionanogenomics. At least one of them. It's a no-brainer. They have to. They have to. They have to try uh, because the genomics fight for taking a bigger market share is on. Is on, and they are elbowing each other. Illumina, Thermo, PacBio, they are elbowing each other, and QIAGEN is doing it too, and Oxford Nanopore is doing it too. So the key of Oxford Nanopore, if you don't know anything about it, is that they have a device the size of this that you can plug into your laptop, and that thing is what is going to sequence your genome. So you don't need a whole machine the size of a fridge. You only need something that is this big, the size of a USB key, right? To plug it in your laptop. So you can. Why do you want to sequence something in the middle of the jungle? Well, let's say that you have some sort of tree there, or you cannot freeze the sample or to take it into your lab and take it and get into a plane. So that offers a lot of advantages to go mobile. Why do you want to go mobile? For the same reason I have this. For that reason, you want to go mobile, right? So let me see if I can answer the last questions. BNGO is right down the street from Illumina. That is one thing. So that is an advantage if you want to look at it. Bionano is 5 minutes. Yeah, same thing. Is there other mapping company? Not that I'm aware of that works with the same thing. But for example, if you do karyotypes, a karyotype is a sort of mapping, and the way you map is by looking at the bands in the karyotype. So if you look at a karyotype and you type in, for example, karyotype in Wikipedia, you will see that what represents a chromosome is represented as well into bands. Those bands and the way they are organized into the chromosome, that's a way of mapping. But you have to do that by eye. And there's software and there's other tools that can help you that. But it's not as straightforward and as with the detail that you can have with the Safari system, which makes this circle plots that you see, that is integrated in the system, and it gives you a quantitative number as well. So the analysis is much easier. Do you think that it will be better for our pockets if BNGO is acquired? It seems like it will be better if BNGO grows their own. You mean in stock, from the stock perspective? I don't know. Depends on the offer. Because if they say, hey, we're going to buy Bionanogenomics for $100 million, I don't think it's very good. But if they say, hey, we're going to give you 20 billion, I think that will be a good offer. And it will be better for investors than if they say, we're going to give you $10 million and what they think is worth. And also depends on what they want to do in clinic, because the market that the Sapphire is going to disrupt, is about to disrupt, is different than the sequencing. It's different. It's a quick and accurate tool to give you a genomic landscape. That's what it is, and you can translate that into mapping in the clinic. So if you go, you have your sample analyzed, and a few hours after, you get the results in your phone. That's what it does. So their business of the other companies is in the sequencing. But the sequencing works different in academia or research laboratories than in clinic. In clinic, they don't necessarily want to discover anything new. They want to provide a service. And that's it. They follow the protocol. If it's not on the protocol, we don't do it. In academia, it's different. In academia, you figure out what you're looking at, and you try to discover something new on research labs or R&D. So it's a different type of business. So I'm not quite sure if any of these other companies that might make an attempt to acquire BioNano might want to go into that. In my opinion, the one that is obvious is Illumina, because they have already one sequencer that is FDA approved. So they want that. And the business model for BioNano Genomics, apparently, it became more of a consumable business model rather than selling the machine. Selling the machine will be secondary for the business model. So Illumina already does that. So to me, the most obvious play is Illumina. But to me, with the ignorance that I have so far. Let me see. Awesome to work on nanonodes. Yeah, I mean that's the promise. I mean, since I started doing science, uh, people have said that the $1,000 genome fully sequenced is the goal. That was the goal 20 years ago. Today is not the goal anymore. The goal will be $100, and when we get to $100, will be $10, and so on and so forth. Just like today, I don't know, 120 megabytes of memory is not enough. It has to stop. It has to stop because not many more people became customers. But as there are more customers, the price is going to get lower, I think. And this is why I think it's good that Jennifer Doudna and Emmanuel Charpentier won the Nobel Prize. And it's good that RG is making noise about genomics because many people are interested suddenly in genomics, either because the word is fashionable, or because it's the future, or because they actually want to become a player in the genomics field. So I think it's good, and I think we are on the right track for that. OGM is here today. Imagine where OGM. Okay, that's another question. Let me see. Polycystic kidney disease, dominant. I'm sorry to hear that. And wants to get pregnant, but a doctor said no, since she will give complications. Went to gynecologist and use yes, absolutely. So if you're looking for questions and the PacBio or Illumina can give you the answers, go for it. Go for it. If they don't, separate, combine them, and go for it. Because that is what can give you the answer that you're looking for. So you better decide the steps you want to follow. In all due respect, Illumina is FDA approved for a specific application, not blanket approved for the machine. I don't think by now is for sale. Maybe a partnership is possible. Okay, what I can promise you is that I'm going to look into the details of that. Machine of Illumina. And if you guys want, and drop a like so I know that this talk was useful, what we can do is I can give you the details exactly of what I'm talking about, because you might be right, I might be mistaken, and it's not for a specific application, but I can promise I can look into the details. And the purpose of this is to try to clarify stuff, not to make it more confusing, right? So I wouldn't be doing my job if I make it more confusing. So I can promise that. And if we have another session some other time, in a week or two, I can try to clarify that. But thanks for pointing it out. Does anyone have any other question that I can try to answer? If not, I will close the stream here. Does it should work together? I think they will have to work together at some point to try to integrate the BioNano results to a sequencer. That's the future, I think. Which sequencer technology is going to be, that I don't know. But it will be exciting. I mean, people of them with the sequencing results. They already do that in academia. So I don't see why not. This can be coupled in a single vertical stream for newbies, right? So I don't think why it's not possible. So great. Then thanks a lot. If you found this useful, drop a like. And if you guys want, we can try to shoot for another live stream in maybe a few weeks or so. In the meantime, stay safe, enjoy the market, and try to learn as much as you can about genomics. If you have more questions that were not being answered here, try to prepare them for the next session when we have them, so I can be more straightforward to that point without a lot of other stuff, nonsense stuff that I talked about. Okay, well, thanks a lot and have fun.